Hello everyone. This video is part of my final thesis presentation in computer and system science. My thesis focuses on the implementation of machine and deep learning algorithms for a classification task provided by Scania, a leading truck manufacturer. The title of my thesis is Neural Networks for Predictive Maintenance on Highly Imbalanced Industrial Data. In this video, I will delve into the coding techniques that allowed me to present multiple solutions for the classification task. To accomplish this, I will be utilizing Google Colab, where the complete project is located. This will allow anyone to explore further details. Please note that I have employed a publicly available dataset for this project, and I have provided the link to the UCI repository along with other solutions presented on Kaggle. Any practitioner will notice that I am avoiding sampling techniques, and that is on purpose because the thesis wants to introduce a novel approach to the problem. And here I confirm that sampling is another valid approach to the problem which is not conflicting with the ideas proposed here. Finally, I want to mention that I am grateful to my supervisors, PhD student Ali and Professor Sindri, for their guidance throughout the study. With that said, let us begin. To understand our project, we need to understand our problem first. So what we want is to predict failures on the APS. APS stands for Air Pressure System and is the system in charge of providing pressurized air to the braking system of the trucks. Therefore, is a critical component of these vehicles. For that, Scania is telling us that there's a different cost on the misclassification of each truck. For false negatives, we have a cost of 500 units. For false positives, we have a cost of 10 units. What is a false negative? A false negative is when we say that there is no failure in the APS, but actually there is. And a false negative is when we say that there is a failure in the APS, but is completely fine. So we can say that 500 units is the cost of letting a truck go away without checking the APS, and there is a mistake. And 10 units is the cost of unnecessary checks. Then that's the problem that we have at hand. And here's the first thing to keep in mind, that there's difference in, we need to include cost-sensitive analysis because misclassifying false negatives has a very different cost to misclassifying the positive label. It has a very different cost to misclassify the negative label. Then the data. The data that we are using comes directly from the UCI repository. We can explore a bit how it looks here. If we ever open the UCI repository, we'll see that the first column is the class label, negative or positive, and the other ones are readings from different components from the trucks that we want to combine to predict if there is or there is not a failure in the APS. So in total we have 171 columns, attributes, or features, however you want to call it. So, and that's the data. Here in Kaggle, you can see other implementations which have different approaches and still solve the problem. So this is the implementation that we present in Python. And these are all the libraries that we will use in our project. Here we don't need to dive into the details. All the details are given in the project. But let's continue here. So here our project starts. So the very first step that we do is to import the data that is given in the UCI repository. As we see in Excel, we have the class label says neg and pos. So to follow good practices, we will change that by 0 and 1. And that way we can be in line with good practices. We explore how many instances of each class label we have in the training and test set. For training, we have 59,000 of negative class label and 1,000 for positive class label. For training is 15,000 and 300 respectively. It means that we are facing an issue with the class imbalance, and this is very typical in real-world applications because industrial companies, they have well-functioning machines that are reporting data all the time, and just a fraction of them fail, and is the ones that we normally are interested on. So real-world applications, normally we will face class imbalance and also cost sensitivity, as mentioned before. Think about medical applications where you want to discover the patients that have cancer and the patients that they don't have cancer. Hopefully, we will face a situation like this one, like the big majority are healthy people and there's just a small fraction that are not healthy, and we want to discover as soon as possible. Same happens with machines, same happens with cybersecurity, and yeah, most of the real world applications present this type of problems. Yeah. So if we continue, we clean the data. The very first part that we notice is that there's a very big amount of columns that have a lot of missing values. So it means that this is a missing value. When we check this, there are columns that the big majority of the column is NA. And in this case, 12,000 instances out of, let's take a look, 16,000, so more than 50%. This type of columns, we want to remove them. They will, if we leave them, then they will create a lot of noise into our project. So what we will do is to drop those columns so we stop working with them and exclude them from the project. So our classifier will not learn a lot of missing values. Yeah, we continue we analyze all the attributes that we are given, and I want to mention here that Scania anonymized the dataset. So even if we have column names like AA000, like all of this, Scania does not tell us what is that. And yeah, so therefore we are working with a 100 model which is agnostic, doesn't know anything about the data, but we can discover a couple of things. For example, in this case, we can see that for this column, the one which is here, the B, we have very different values for the positive label and different values for the negative label. My impression is that this could be the age of the truck or the mileage of the truck, how many kilometers it has been driven, and that will affect if the APS is healthy or not. So here I plot several columns, one against each other. Of course, plotting one column against other is not telling us the complete picture, because, well, we have 170 columns and we have dropped around 20. So we are working with 150. So for that, we continue, and then we need to do following good practices. We need to do data scaling, putting all these numbers in a scale between 0 and 1, but keeping the proportions. And then we need to do data imputation. It means that columns that were not dropped in previous steps, now we will change the missing values for a mean, meaning that we will go calculate the mean of the whole column and we will replace the missing value. Okay, and then we will remove the anomalies. The outliers will be removed, just because classifiers tend to help better with when you remove the outliers. And finally, I'm thinking about that plotting two different columns does not tell the complete picture. We use TSNE, and we plot, we reduce data that is high dimension. In a high dimension, we reduce it to 2 dimensions, so we can make a scatter plot. And this is telling us that yes, we have a very big class imbalance, but also here are clusters. We can see that TSNE can actually cluster some of our of the positive class clusters here in this area, although we have some outliers, some trucks that were clustered here, for example. And most likely we don't want to, this would be very difficult for a classifier with this data to predict that this truck is positive and has a failure in the APS. So we present different different visualization techniques to understand the big picture of the problem. And here we use UMAP and it shows exactly the same. There's a big class imbalance where we can see that class label 0, negative, it is all over the place, and class label 1 is smaller, more focused in one place. Yeah, so here. Now, we start to create models. In our project, we create 3 different models, machine learning, and 3 different models of deep learning. For that, we can jump here. Initially, we create one model using a random forest. Random forests will try to learn using the training set, the 60,000 records, and then we'll try to classify using the test set. And when we check the results here, we use the test set to classify, and we come to a total cost of 14,450 units. And after classification, it means that it learned a lot from the training set, and it was able to predict the test set to a certain extent, actually. So let's see the misclassification. So the random forest managed to properly classify 14,000 records of the negative class. It managed to classify 360 records from the positive class, and it misclassified 13 records from the negative class, no, from the positive class, meaning that there was actually an error in the APS, but our classifier said that there was no error, so the truck left the workshop without being checked. And this one is 700, okay, 800 trucks were checked unnecessarily, meaning that there was no failure in the APS, but our classifier said that there was an error. So when we multiply 13 times 500 plus 800 times 10, we get the total cost presented here, 14,450. So if if we want to know more or less which has been done before us, baseline classifiers. When we check previous implementations, we realize that this is a very good result actually. Just one second. Here. These are previous solutions to the same problem, and we realize that we are very close to scientific papers that they have tried to solve the same issue. So we are reporting 14,000, and there's others, and it's in line with previous research, a bit above. But this is just the very first classifier we're showing. And here can continue. And then we use LGBoost, another classifier, and try to make a better classification for the same problem. In this case, we misclassify 11 trucks from the positive label and 846 trucks from the negative label. Total cost 14,000. We are still very much in line with previous scientific papers, still above, but we can continue with another classifier. Here, logistic regression, and then we managed to reduce that cost just a bit, so we are still below 13,000, and yeah, very similar results to the one presented above. You might be wondering, what is this? This is all the 16,000 trucks that we are trying to predict. We are plotting how sure is the classifier. So if it's very close to 0, it means that the classifier is quite sure that it belongs to the negative class. If the prediction is close to 1, means that the classifier is quite sure that the truck belongs to the positive class. The red line indicates the threshold that we are using. So if we change this threshold, for example, 0,3, it means that anything below 0,3, it will be classified as negative, and above 0,3, it will be classified as positive. But then how do we come up with this number? This number, we are calculating it. We are making a calculation and then try to find the best threshold for the specific classifier. In this particular case, we use 0,36 for logistic regression. If we come to for LGBoost, we use 0,45. And then if we go above, actually we can erase this part. If we come above, for random forest, we use 0,44. But, so if we check, we are not coming, we are still not matching previous research. We are a bit above other scientific papers, other solutions that have been presented. So what we are doing with the three classifiers, the random forest, LGBoost, and linear regression, now we will combine them. And in machine learning, that's called ensemble. So we are creating an ensemble using the three different classifiers. And what we will do is that in a majority voting, we will say which is which, to which label will belong each one. And then here we go. When we combine the three classifiers to come up with a better idea, we go down to 11,000 in total cost. And if we compare to previous scientific research, we are then making it better than other authors. Still, these two are much lower, but we beat all of the rest. And yeah, that's an implementation with machine learning, trying to face cost sensitivity and class imbalance at the same time. But now we also, our thesis is called neural networks. So this part was just for learning, for getting to know the data. Now we jump into the neural networks for the classification. So we create our hypermodel to do the tuning of hyperparameters, and yeah, after running, in this case I run the model 15 times only. I would recommend to run it much more times, but this will demonstrate what I mean. I run it with the idea of finding the best combination of hyperparameters for the classification task. So, but in this case, when we take a look, we use a traditional neural network, and we managed to, yeah, this is a bit worse than the previous classifiers, but this is not the solution that we are presenting. If we take a look below here, we create another hypermodel. Okay, but before we continue, I want to mention why is this getting worse. Is because a neural network is not optimized for class imbalance. The big class imbalance will make the neural network to focus in the big majority in the negative class, in the majority class. So for that, we are proposing a change in the hypermodel. Here we are proposing to use to use a different loss function, and we propose a loss function called binary focal loss, and the normal ones, the normal neural networks, they use binary cross entropy loss function. So we move from binary cross entropy function to focal loss function to see if we can get better results. There are several parameters that can be tuned, but we don't tune all of them because Google Colab does not have, we are using Google Colab, the free version, and then we cannot, the speed is not the best. But here we create another hypermodel, and the result of the hypermodel is that, yeah, so we jump from 17,000 to 13,000, going down again. And finally, we create another neural network that, okay, 14,000. Finally, we create another neural network, and this time we are using the normal binary cross entropy function, but we change the evaluation metric, and we use as evaluation metric F1 score. These practitioners will understand what I mean. In the very first one, we use binary cross entropy, and we use accuracy as evaluation metric. And in the second one, we use focal loss and accuracy as evaluation metric. And in the third one, we use binary cross entropy as loss function and an F1 score as evaluation metric. When we check the predictions, we come to 14,800 units. So what if we combine the results of our three different neural networks in an ensemble, as we did before? When we combine the three results from the neural networks, we can come to a total cost of 13,000 units. But that's in line with previous research. So our solution is around 13,000, 12,000 so far. But we discovered in our study that we could combine the results of neural networks. These two are neural networks. And when we combine it with one normal classifier of machine learning, the cost can be improved a bit more. So for example, here we combine a normal neural network with focal loss and random forest, and we come to 12,000 in total cost. And for example, here also we combine with LGBoost and two neural networks, and we come to 13,000. So far, the very best one that we reported in our studies, they were the combination of three machine learning classifiers. Let me see if I can just find it. Here. Here. Yeah. Reporting 11,900, which beats several of other implementations, but does not beat these two classifiers which are here. So to understand a bit of the background, this is the best classifier ever reported for this problem, so we are quite close anyways. And this is a study from Scania together with a master thesis student, but they did it together. So this might not be a model agnostic model which is agnostic. Well, this one is the best ever reported. So yes, so that's the code and the implementation. We did not stop that much into the details because the code has a lot of comments and explanations. But before we close this video, I would like us to think about the intuition behind the problem. So let me see if I can just okay, here. If whenever we read the thesis and we think about it, we are being asked to classify 16,000 records between positive and negative. And if we would ever try to classify them manually, like without using deep learning or machine learning, we could easily face a total cost of 160,000, 192,000 without using these techniques. Would be pure guessing or a bit of previous knowledge. Still, the total cost would be very high. Using machine learning and deep learning, we are reducing this total cost to around 10% of the naive approach. That is what we have presented here. Yeah, so 11,900 compared to 160,000 or 192,000. And that's a big improvement. Yeah. Somebody that is a practitioner will think that, hey, what about the sampling techniques? But the sampling techniques were not used because we wanted to use a novel approach, a different approach to the sampling, which is the standard way of fixing the class imbalance. But yeah, I hope that the coding that I am giving together with this video will allow any practitioner to replicate the results that I am given in my thesis. I did not dive into the details because otherwise it would become a very long video, but I hope the intuition can help to anybody who wants to continue the study on this topic. And also in my thesis, which is in Google Colab, I propose different ways to continue to even improve the classifiers. I propose 3 different ways. Yeah. So I hope this helps to any person, whoever faces issues like this one with classification task with with class imbalance and cost sensitivity. And yeah, thank you so much. Bye bye.